welcome to part 2 of Earth's natural energies. This is a 3-part series I've been putting together. Part 1 was about telluric currents. This part will be about atmospheric electricity, and part 3 is where things get really interesting. That's rocks as batteries. So just as a reminder, the reason I'm putting together this 3-part series on the various sources of Earth's natural energies is because in this channel and with this series, I want to start to kind of piece together some of the mysteries around the purpose of these ancient megalithic sites. So on the far left, we have Northern American mounds, and then in the middle, an example of, a stone wall in South America, and then of course on the far right, over here, we have the Great Pyramid of Giza. So the hypothesis or the thesis of this channel is that these ancient constructions are designed to concentrate and amplify Earth's natural energies for the promotion of biological life. Okay. And if you're wondering, well, what are Earth's natural energies? I mean, these are just simply electromagnetic waves. And in all these parts, we're just describing how current is moving, how, electric fields are forming, and ultimately it's all electromagnetic phenomena. So that's the goal of this channel. And a little recap of what happened last time with telluric currents. What I did is I kind of explained this theory called the magnetosphere dynamo. And what that is if you just imagine the Earth spinning on its axis, and of course it has a magnetic field emanating from the core, and every time from the reference point on the surface of the Earth, every time you go into the sun's energy at dusk and at dawn, the solar wind actually exerts a force and compresses the magnetic field lines coming from the Earth. And on the far side, where the sun is not, they expand and relax. And this is an impulse that happens at dusk and dawn. And basically, when you compress these magnetic fields, the magnetic field lines from the Earth, you are pushing a current. You're going to generate a current through the principle of induction. So you're going to induce a current at dusk and at dawn during these transitions to flow around the globe. And of course, these currents, they flow where the Earth is most conductive. So it's common for them. So that's why an aquifer is so important. And we're going to get into aquifers a whole lot more because they're really important for where you place megalithic sites and temples and churches and all that. And this is obviously where water can accumulate and flows into and out of. And so water is a good conductor, and that's why these telluric currents generally kind of flow where there's water in the Earth. Okay, but today we're here to talk about atmospheric electricity. So, where to begin? Previously, as I just described, we were talking about the sun, the solar wind, its impact on the magnetic fields from the Earth. Okay, so now we're going to talk about the sun and the solar wind, or solar radiation, impact on the atmosphere right here. Okay, so it also has an impact on the atmosphere. What it does ultimately to the gas in the atmosphere is it ionizes it. So pretty simple. So what is ionization? So basically the sun's energy is going to come in. It's a wave. It's an electromagnetic wave. And if it has enough energy, there's going to be, let's say, a gas molecule in the upper atmosphere. And this photon of energy is going to come in, and if it's enough energy, this molecule of gas is going to absorb that energy, and it's going to kick off an electron. So when it kicks off an electron, as it does right here, you get a free electron floating around, and then the nucleus is positive. So if it had two positives and two negatives, then it would be neutral. Now it kicked off an electron, so this part is net positive, and this part is this free electron is, of course, is obviously negative. So that's ionization. So now you have two charges floating around, positive and negative, and the charges will be able to follow the magnetic field lines of the Earth, and they're going to go to the North Pole right here, and that's why at the North Pole you get all these charges being accelerated in Earth's magnetic field, and they collide with other gas molecules, and that's enough energy to kick off other electrons. It's the process of ionization, and it emits light. Okay, so the point is that the sun causes ionization of the gas molecules in the upper atmosphere. Okay, so why is this important? Well, imagine being down here at the lower parts of the atmosphere. Okay, the gas is really dense down here, really dense. Okay, up here in the upper ionosphere, the gas is much more spread out. So why this is important is because when the process of ionization occurs and you have the solar radiation kicking off an electron, normal circumstances would have it just probabilistically that this positive ion, an ion just simply means, a positive or negative. It has a charge. It's an ion. So under normal circumstances in the lower atmosphere, this positive and negative will recombine and become neutral again. But when you're floating up here in the upper atmosphere, it can happen where you get a separation of charges. So what you might see, and what it's proposed to be, is that charges tend to separate, and you get positive charges forming in the lower ionosphere, and you have negative charges higher up. And these electrons are what allows these free charges are what allow the ionosphere to be conductive. So a conductive ionosphere is really important. Imagine, again, here we have some positive charges, and then we have some free electrons floating about, and because it's such a decompressed gas up here in the atmosphere, they're not just instantly recombining and canceling each other out. So now they're able to slosh around and be free. And what does that mean? It means that the ionosphere is conductive. And the effective consequence of this is that for radio communication, you can direct an electromagnetic wave, a radio signal, up into the upper ionosphere, and it will bounce off the ionosphere because it's conductive, and it will go back down to Earth, and that's how you can communicate with people across the Earth, whereas if you just did it like this, it wouldn't get across. So it's actually key for global communication. Now, you can think of the ionosphere as this cavity where we have a conducting shell here and a conducting shell here. The Earth will say it's negative, and this part of the ionosphere will just say it's positive. And you get these frequencies that are very distinct frequencies. So here we have 7.83 hertz, 14.1 hertz, and 20.3 hertz. These frequencies are harmonics because when we have this cavity, there's only a certain discrete wavelength that's going to be able to fit and resonate inside this cavity. And here are those wavelengths depicted. And they're called Schumann. I don't know if that's actually spelled correctly, but this is called Schumann resonance. Okay, so the atmosphere, it does have many different regions to it. It's proposed that the lower region is positive. And who proposes this? The global electrical circuit theory. It's a theory that you can go ahead and look up, and it's proposed that the surface of the Earth, is overall negative, and the lower ionosphere is overall positive. So I just drew a positive and a negative with the atmosphere in between them, and the atmosphere can be thought of as a insulator. So some of you might recognize a symbol like this, and that of course is a capacitor. So the atmosphere is like a giant capacitor, and what a capacitor is if you've ever unplugged your device and you've seen your LCD screen still lit up, or maybe you have one red LED on it and the LED is still lit up even though you unplug the device. Well, it's because you have this component somewhere in the circuits of that device, a capacitor, and a capacitor is effectively just a battery of sorts. And the way this works is the capacitor has two plates. One's positive, and one's negative, and it's separated by dielectric, so an insulator. So you can see this is totally analogous. We have positive charges in the lower ionosphere. And why are they in the lower ionosphere? Well, because they are attracted to the negative charges that are on the surface of the Earth. So that's negative, and that's positive. So now between these charges, we have the atmosphere. And the atmosphere is semiconductive. It's not very conductive, but it can conduct a little bit. So you are going to see a movement of charge. And the way an electric field is depicted is from the perspective of the positive charge. So the positive charges, opposites attract. The positive charges, of course, want to go down to the negative charges. And so what you end up with is an electric field. And so that's what atmospheric electricity essentially is it's the sun driving through its ionizing force a charge separation between the ionosphere and the surface of the Earth. And this sets up an electrical potential of 3,000 volts, which sounds like a lot, but it's really not that much. It's actually, it's not trivial to extract energy from this. You can, and it's just not a lot. So it's a lot of volts, but it's not a lot of amps. So this is a point where I want to make clear that, this isn't the end-all be-all, because we still have a lot of uncertainty we're dealing with, a lot of unknown. If you just do some very basic Google searching, I asked what is the polarity of the global electric field between ground and ionosphere. So literally what I was just discussing, and you just get the result, the polarity is uncertain. I mean, yeah, it's crazy, but we don't even know if this is actually true or if the complete opposite is true. Now, it almost doesn't matter. It definitely does matter, but just the fact, even if these two charges were reversed, we would still have the same magnitude of the electric field. It's just nice to know which one's which, and we'll get into that later in another video. But according to the most common theory, it's as I showed. The bottom of the ionosphere at least is positive and the Earth's surface is negative. So this is the common thinking. So I ask another question. I type in Google, is Earth's surface positively charged? And of course it's not. I mean, they say Earth's surface is negatively charged. And then they go on to say the reason why the surface of the Earth is negatively charged remains to be clarified. So, okay, it's saying, well, it's negatively charged. We don't know why. So it is probably negatively charged, who am I to question these things? But it most certainly can be positively charged as well. And in fact, it can be overwhelmingly positively charged. And we're going to get into that later. But even just right now, as we continue with this video, you'll see that during a thunderstorm, the Earth's surface becomes very positively charged. And there's, of course, no explanation for that provided as well. I mean, it's just very frustrating doing this research because there's so much we actually just don't know. So, but we do know atmospheric electricity is real, of course. So forget these details. I mean, this is a real effect. You can see these guys are flying a kite and they're interacting with the string.
Watch the string going up. Look at the side. Look from the side.
So this string is, of course, has a static charge on it. This has the feeling of static electricity, a little corona discharge, and this guy on top of the mountain, corona discharge as well. And he changes the way his hand is shaped, and it changes the pitch of the sound. So that's a great indication that, this is a corona discharge of sorts, and it's occurring because you're in the presence of a high electric field. So the electric field is really extreme up at that altitude, and you also have a lot more ions available at that altitude. So it's time to get into lightning. According to the global electric circuit theory, lightning is totally essential for two things. It's said to be responsible for charging the Earth with the negative charge. So if you asked, well, why is the Earth negatively charged? Why are we saying that? Well, because we have lightning giving electrons to the Earth. This is what's proposed. This is not really what I'm proposing. You also, when you have lightning strike, it also emits electromagnetic waves, and these electromagnetic waves actually are the origin of Schumann resonance. So that's also what's proposed. Generally, if you just do any sort of basic research around this, these are the answers you are given. So yeah, you got to have that picture in your mind of, this is conductive and this is negative, and then it's going to bounce around, and it's going to go all the way around the globe in the cavity between the ionosphere and the Earth's surface, and it's going to create those harmonics and Schumann resonance. Okay, so we want to talk about lightning, and lightning is yet another one of those things that is going to be very challenging to explain because we just don't know a lot. That's the problem with this, is we're not sure about a lot of things. But what is a great experiment to have a look at is called Lord Kelvin's thunderstorm. So this is a really old classic experiment with water. I'm going to play this video.
In the 1930s, Victor, and later his son Walter, experimented with the so-called Kelvin generator. When falling through copper spirals, thin strands of water produce high electrical voltages. Tiny water droplets suddenly change their direction of fall, contrary to the laws of gravity, and move back upwards. This levitation is a phenomenon that had already been investigated in the 19th century by the Nobel Physics laureate Philip Leonard at waterfalls in the Alps. The tiniest water droplets carry an electrostatic charge. They form a very fine spray that can easily be seen and inhaled. Waterfalls have a positive effect on human health, particularly.
Okay, so you can induce a charge on water, and because these copper electrodes are charged, there's an electric field around them, and because you've induced a charge on the water becomes attracted back upwards. So you can induce a charge on water. Now, I'm not saying this is how a thunderstorm or how a thundercloud forms or how it works, but I mean, it certainly gives you an indication of how this could start to make sense. So I'll just explain how this works really briefly. You have water that drips out from two nozzles here, and it drips through an electrical conducting tube, a coil, or just a sheath, a cylinder of copper, something like that. Okay, so each side drips through its own one, and these are attached to an opposite container where the water ends up. Okay, so in the explanation of how this works, you basically just accept that there's going to be at the very beginning of the experiment a bias. Either this one's going to be a little bit more negative than this one, or this one, or vice versa. But let's just take it as a truth that when you start this experiment, this left hand coil happens to just be slightly more negatively charged than the right one, just random. And that slight negative charge induces the opposite charge in the water droplet, a positive charge. That positive charge gets transferred to the receptacle bucket, and then because it's attached to this wire, it goes over to this one and induces a positive charge on this one. And then that induces a negative charge in the water droplet. That falls into here, and because it's attached by a wire, it induces a negative charge on that, which reinforces the positive charge on that. And so it's like a reinforcement system where it just gets perpetually higher voltages, and it's enough voltage to create a spark gap. So you'll see an arc of electricity. I wish I actually had that in this video, but yeah, you see an arc of electricity. So there's actually electricity in water. So that's why it's called the thunderstorm, is because this is an arc of electricity. And what we have in a thundercloud are, of course, arcs of electricity. Now, like I mentioned, we're not going to be able to do this justice, but I want you to be aware of in a thundercloud, you have a downdraft of cool air and an updraft of warm air. And what it's doing is it's pushing water from a transition phase. So you have moisture in the cloud that's cold, that's rapidly becoming warmed up. And it undergoes like a phase transition. It's like icy, it's almost like icy water droplets. And this, like the experiment I showed you, Lord Kelvin's thunderstorm, what it ends up doing is creating a separation of charges. You have negative charges that form at the base of the cloud, and you have positive charges that form at the top of the cloud. Okay. So this is like so much of what we talk about with Earth's natural energy is the separation of charge for one reason or another. So remember, we're in an ionosphere right now. This is the separation of charge taking place. Okay, so that's the electric field of the atmosphere. And then this cloud, this thunderstorm, is another separation of charge that's occurring. And the way it's proposed to work is you have lightning that can definitely opposites are attracted. So you'll have lightning going from the top to the bottom of the cloud, or just within the cloud structure itself. But of course, you have lightning that comes down to Earth. And notice that the bottom of the cloud is negative, and I just got done telling you that the Earth's surface is negative. So opposites attract. So why would the negative base of this thunderstorm discharge into a negative surface? Well, it doesn't. So a bunch of positive ions just show up on the surface of the Earth. And what happens is these positive ions, positive charges, they actually, if you were to watch lightning carefully, it doesn't just come down from the sky to Earth. It comes down from the sky, from the cloud, towards Earth. But then what happens is positive charges actually jump out of the Earth to meet the negative charges coming down from the cloud. So it's a subtlety, but I mean, it's really interesting that, the theory is that the Earth is negative, but then all of a sudden when you have a thundercloud come through, okay, well now the Earth is positive. And it's just, well, how did that happen? What's the theory behind that? So that's what we need to, or that's what we're going to dive into in part 3.